All right, good morning, everybody. 2 days of school remain, and we have this remaining 2 days, two new sets of lectures for you. One dedicated to jets, heavy ion collisions, one dedicated to entanglement. And so Yassin Mehtar-Tani from Brook National Laboratory starting his set of lectures telling us about jets and heavy ion collisions. The floor is yours.
Thanks. Good morning, everyone. So my task this morning is to give you an introduction to the topic of jets in heavy ion collisions. So I'll have to introduce the concept of jets broadly, and then, of course, motivate why we want to study jets in heavy ion collisions generally. Okay, so this is the outline of the lecture. I make it so part of it will be done today, and the other any leftover will be discussed tomorrow. So I'll start with it can be divided into three parts. So I start with the introduction, the context. Then I'll discuss the elementary processes. So I'll try to introduce to you what are the elementary processes that we need to account for to understand how jets interact within a hot QCD matter, which is the coagulant plasma producing heavy ion collisions. And from there, once I've discussed the elementary processes, which are radiative processes and elastic processes, I'll show how we can use this knowledge to understand the physics of jet quenching, which is observed in heavy ion collisions. This is for the this will be discussed in a parametric way, so it will be rather intuitive. And then I will try to introduce for the theorists among you and also for the experts who want to understand the techniques, the basic technique that is used to perform calculations in this field. And eventually, I'll revisit the discussion of radiative energy loss and the nuclear modification factor in the context of this method to show explicitly, at least give you a flavor how calculations are done. Okay, let me start with the introduction. So 20 years ago, at Brookhaven National Lab, a few miles away, we started conducting ultra-relativistic heavy ion collisions. So this is a depiction of the different stages of such a collision. So picture two heavy nuclei, like two lead nuclei or gold nuclei, accelerated and accelerated to a speed which is close to the speed of light, right? So of course they're Lorentz contracted. This is how they look like before the collision. Right before the collision, these are the two nuclei. They collide. This is time 0, and all of this kinetic energy will be transferred into and transformed into here in elastic and into production of a lot of particles. So right after the collision, a lot of partons, gluons and quarks are freed. So all of this energy is transformed into the production of particles, thousands of them. And they start strongly interacting. So the energy density is very high. So strongly interacting until they reach a state of roughly thermal transient state of thermal equilibrium, which we call the coagulant plasma. Of course, the system keeps evolving and diluting and expanding until, of course, all of those partons, quarks and gluons that are roaming freely will hadronize, the system cools down, and then have hadrons that fly, that are not interacting anymore and fly all the way to detectors. And this is what we see at the level of the detectors. So this was, again, this coagulant plasma, which is the hottest matter in the universe, was discovered at RIG, as I said, 20 years ago. And the basis of this discovery is the study of these two types of observables, bulk observables, where we just measure the particles and how they behave, the soft particles, so this bulk of particles, how they behave, basically they behave collectively, which translates the fact that there are strong finite state interactions. And of course, the second part, which would be the subject of this lecture, is through the quenching or the suppression of energetic particles in the finite states, which is also a reflection of the fact that you have we have produced this hot, dense QCD matter. All right, so what are the energy densities we're talking about? So this is just an estimate based on lattice simulations. So we know from lattice simulations, so this is the QCD energy density as a function of the temperature, that initially you have just gas of hadrons, that after a certain, which you heat up, which at the given temperature, which is of the order 170 MeV, not GeV, of course, it is a typo, the system undergoes a phase transition. It's a crossover phase transition. And the number of degrees of freedom increases. So we go from hadrons to partons and gluons. So of course, gluons and quarks have more degrees of freedom, color, charge, and so on and so forth. And this will translated into this increase in the energy density. So the estimate here, this happens at the energy density of the order of half GeV per Fermi cube. All right. So this limit here, this is the Stefan-Boltzmann limit that can be calculated by just assuming, of course, free gas of quarks and gluons. All right, so at trig, this is the typical type of estimate of energy density that is reached there, which is above this transition temperature here, this critical temperature here. So then we expect, that's why based on this estimate, we can expect the formation of the quark-gluon plasma at trig and also at the LHC. So I mentioned two major type of observables that hint to the production of this quark-gluon plasma. So the first one is by looking at the flow harmonics. So what typically we do, we look at the momentum distribution and the azimuthal distribution of the bulk of the particles produced in heavy ion collisions. And we look how they behave. So in particular, we look at the average of the cosine of this the azimuthal angle of the particles with respect to the reaction plane. So this cosine modulation is a reflection of momentum anisotropy in the final state. So if there's a momentum anisotropy, it means that strong interactions in the final states that led to the, or collective behavior in the final state led to this kind of anisotropy as somehow a transfer from spatial anisotropy. As you can see here, you have this kind of peripheral interactions, not head-on interactions, where you produce this kind of almond shape form of matter. So initially, the momentum distribution is isotropic, but due to collectivity and final state interactions, this isotropic momentum distribution would become anisotropic, and you'll have higher momentum particle flowing along the reaction plane as opposed to the perpendicular to the reaction plane. And this is captured by this kind of observables, the flow harmonics. So calculations based on hydrodynamics or viscous hydrodynamics explain very well and describe very well the data. And the viscosity to entropy ratio that is extracted from the data is very small, very close to the certain limit, lower limit bound that was derived from gauge gravity duality calculations some time ago. All right, so we have this kind of perfect liquid. So we know that now the quark-gluon plasma behaves strongly interacting matter, which behaves as almost perfectly. So now, of course, we have this kind of feature that we kind of extracted from the data by studying bulk observables. But we know that the coupling runs in QCD. And QCD matter behaves differently at different scales. The quark-gluon plasma can be viewed at very short distances as a free, as a gas of quarks and gluons that are freely roaming and weakly interacting. Right? So how do we go from now a strongly interacting quark-gluon plasma at relatively long wavelengths, and if you increase the resolution, we should expect to see different features, different QCD dynamics, all the way down to quasi-particles that are point-like particles that, as I said, are weakly interacting. So this is one of the questions that we would like to tackle by studying more in a more refined way the observables and the dynamics in heavy ion collisions. So the question is, we want to use additional probes that can allow us to go and scan this large range of scales. So we're going to need hard probes for that. So of course, we dispose of this kind of hard probes. In fact, rather sophisticated probes, which are called jets. So what are jets? Where jets are produced in, again, high energy collisions, hadronic collisions, or E plus minus. And jets are pencil-like collimated bunch of particles that are frequently produced in this kind of collisions. As you can see here, you have this kind of 4-jet topology here produced in PP collisions by the CMS collaboration. So the way we view jets, although they are made of collimated hadrons, you can see them as, in fact, a reflection of an underlying protonic process. So looking at a jet is looking at a high energy quark or high energy gluon. They play a very important role in modern precision QCD calculations, whether it's for the Higgs discovery, was really crucial for the Higgs discovery, and it's very important also if we want to dig out some beyond standard model physics. So jets are well understood, and it took, in fact, 4 decades from the discovery of the gluon. Here, DAISY, you can see here this kind of dijet topology, which reflects the production E plus minus going into quark anti-quark pair. All right, so this is what we see here. So this is rather remarkable. We're seeing this two-jet topology. We're in fact staring at the quark anti-quark pair. Even more striking is this 3-jet topology. So the 3-jet topology is indicative of the creation of the gluon. So one of the jets here, usually the fatter jet, is going to be the gluon. So this is, can draw it here. So this is an E plus minus. Rather remarkable discovery. E plus and minus annihilation going into QQ bar there. And then the 3rd jet would be a gluon. All right. So this is, again, 4 decades, more than 4 decades ago. And today we've reached level of precision QCD calculations, which is a few percent, as you can see here. This is a collection of all the cross sections that LHC, but the Atlas collaboration here. And today the technology reached really higher order calculations in QCD that allows this type of precision calculations. Now in heavy ion collisions, we also produce jets. So we have, again, but alongside jets, we have the coagulant plasma. So this is what we see in detectors. So we see a dijet system here. See these 2 jets produced, embedded in a background of soft particles, which again are due to this to the coagulant plasma. Thousands of particles, and then you have 2 jets. So of course, we may expect during the lifetime of this coagulant plasma, which are made again of colored particles, quarks and gluons, the jets, which is also a long-lived color object, before it hadronizes many Fermis, after it is produced, it will strongly interact with the coagulant plasma. And this interaction will leave an imprint in the observable set, where jets will be modified compared to proton-proton collisions. By studying jets in heavy ion collisions compared to proton-proton, we can infer the type of dynamics, QCD dynamics involved in this type of processes, and also properties, transport properties of the coagulant. So the idea of the jet quenching, or using jets to investigate the coagulant plasma, goes back to Bjorken again 4 decades ago, where he predicted the phenomenon of jet quenching. So basically, he conjectured that in high energy proton collisions, provided the energy is high enough, we should produce quark-gluon plasma. Of course, this is not yet achieved at current, or at least we have no evidence, compelling evidence that the quark-gluon plasma is producing proton-proton collisions. But possibly by pushing the energies higher. Nevertheless, here he conjectured that in proton-proton collisions, quarks and high-energy quarks and gluons that propagate through the quark-gluon plasma should lose energy as a result of their strong interactions with the quark-gluon plasma. So this was the kind of the first the idea of invoking the use of jets or high-energy particles in hadron collisions to study the quark-gluon plasma. So now, what is the emblematic observable that is used to indicate jet quenching? So it's called the nuclear modification factor. So what we do, we look at the spectrum of jets as a function of their ET. We look at the yield in nucleus-nucleus collisions divided by the yield in proton-proton collisions and properly normalized by the number of collisions. So if everything happens in nucleus-nucleus collisions the same way as in proton-proton collisions, this ratio should be equal to 1. A difference or departure from 1, especially a number which is smaller than 1, would indicate suppression of jets in nucleus-nucleus collisions as compared to proton-proton collisions. And as I mentioned in the previous slide, such a suppression can be attributed to energy loss of high-energy partons in the jet while traversing the quark-gluon plasma. So then you can see here for jets spanning a large range of scales, almost to the PT, to the GeV scale here, you see very strong suppression, about factor 2 suppression of jets in the most central collisions. So again, this means that really jets interact very strongly with the matter produced in these collisions. So this strong suppression was observed early on at Drake in the suppression of high PT hadrons, and later on at LHC with using fully reconstructed jets. So this is a depiction of what you would, the type of interactions you could see here. So this is a proton-proton collision. This is a dijet system. So here the dijet, once the parent parton is produced, the offspring here will just propagate and fragment independently in vacuum. Yes, please.
So RAA is, essentially the difference between colliding on a nucleus versus colliding on protons, I guess, with the same number. If there were the same number of protons as would be in the nuclei. I guess I understand that this is supposed to be indicative of measuring interactions with the quark-gluon plasma, which would appear in AA collisions or not PP collisions.
Exactly.
I mean, I don't know the lineage of jet physics. Could the difference not occur from jets or the quarks and gluons interacting with nuclei that didn't turn into a QGP? Just the fact that it's going through a full nucleus instead of just a proton?
You could in fact have a possible interaction with suppose you have a collision, right? That doesn't produce a quark-gluon plasma, and then say you just have interactions with hadron gas, right? You could have yes, you have a second question. Let me finish this. So you could have this, but all of the simulations, because of the basically the number of degrees of freedom that exist in quark-gluon plasma, you cannot really achieve this this amount of suppression just by hadron gas.
By scattering off.
Yeah.
Okay.
So it's very
Kernel scan.
exactly, and you could somehow connect this with say other collision systems like Electron-Ion collisions, to kind of benchmark different type of interactions, right? So the strength of interaction is compatible with the interaction with the color system.
There's no data points below 100 PT range for centrality 0 to 10.
Say it again?
No
Too much
points
of-
below 100 PT
Yes.
for the
Yeah. So the reason why we don't have data below 100 is because we need to measure a jet, and a jet is an object that depends on how you define it, right? So you measure particles, but a jet is a bunch of particles that are really somehow clustered together, right? Their PTs is clustered within a certain radius. So you see, you need an algorithm to do that. So we all have an idea, a rough idea what the jet is, right? It's a bunch of particles. But if you want to do measurements, you need to have a precise definition. And this precise definition is not unique. It will depend on how large you want to, the jet to be, the area of the jet, basically how far from this leading partners you want to go cluster particles together. So you have all kind of definitions. All right. So, and because the jet is also embedded in the coagulant plasma, you want to have a precise control over the jet PT. So that you have a certain resolution in your jet PT. And this resolution degrades as PT goes down because the energy density here is very large. So you're looking at really a needle in a haystack, right? You have a small fluctuation, a jet, let's say 100 GeV jet, in a very dense, the energy density is very large. So you have like about 200 GeV worth of energy within the jet that doesn't belong to the jet. So you need to remove that energy. You need to subtract the coagulant plasma away from the jet. Let's say you have a jet embedded in the coagulant plasma. To measure the jet, you need to subtract the particles that belong to the background. So there's a cost to that, which will degrade the resolution. And the lower the PT, of course, right, the higher the resolution cost there. So there is a limit to how low you can go in PT and still call it a jet. You can still tell the difference between the jet and the background. And if let's say you go very low in PT, there's no way to tell the difference between the particles that belong to the jet and the particles that belong to the plasma. And that's why you have to limit this in PT. And of course, this depends on the centrality. As you can see, you can go lower centralities. And the reason for that is because the background is smaller. In less central collisions, you have less background. So you can allow yourself, the resolution is better, so you can allow yourself going to lower PT. You had a question?
Oh, no, I was just going to say that, because Nicholas mentioned like the proton going through the cold nuclei, and actually, I was just thinking of the Cronin effect, where we end up seeing something, instead of a suppression, we see the enhancement.
Exactly.
It's really
Due to multiple, yeah.
Yeah, so it's more complicated than just.
There are interactions with the nucleus, but not.
But as strong as what you would see here.
Okay.
Right. Okay. So, all right. So this is I think a little nice plot here showing a dijet event in heavy ion collisions after background subtraction. Right. So here the background is subtracted. We just measure particles that we think belong to the jet. All right. So this is a leading jet, 200 GeV jet. And then at the wayside, there's a sub-leading jet, which is of the order 70 GeV. So of course, initially, you have a perfectly balanced dijet system due to energy momentum conservation. But because of the interaction with the plasma, one of the jets, simply because you have fluctuations in the position of the jet production, or also fluctuations of energy loss, this would lead to an imbalance in the jet PT. And this is really, again, a reflection of the fact that you had energy loss of one of the jets or both of the jets in the coagulant plasma. In proton-proton collisions, go back here, you would really see two towers of typically the same PT. Okay. So this is just, again, to give you a flavor of the context of this physics here. But what we ultimately want to achieve here is beyond just the observation that we have final state interactions, we have energy loss, we want to be more quantitative. We want to be able not only to understand quantitatively the data, but to extract some information about the matter we are probing. So we want to understand the QGP. We want to understand non-equilibrium dynamics of QCD by studying these jets. So we want to use jets because they are well understood from a theoretical standpoint. We want to use them to really probe this matter here. So you can view it really as study of jets in heavy ion collisions as some kind of Rutherford-like experiment. We are shooting a probe through coagulant plasma, and then by observing the recording particles or the final product of this interaction, we want to infer the properties of the matter that has been probed here. And somehow akin to the Rutherford experiment here, where we shoot alpha particles, energetic alpha particles, through the foil of gold. And then what you can see is that most of the particles, alpha particles, will just go through the foil, and then some of them just recall back. It's indicative of the fact that you have a lot of vacuum, and you have this kind of core atomic nuclei that exist, that occupy a very tiny region of space. This is a very famous experiment, which really, by just looking at the way particles, the probe behaves, we can infer properties of the matter we are probing here. So of course, heavy ion collisions is more complex. Yes?
Quick question. So in the quark gluon plasma, quarks are not confined. Is that the main idea behind it?
Yes.
Okay, thank you.
This is a transient, deconfined matter.
Okay.
Doesn't exist for a long time. It's few Fermi, right? And the hadronization will take over, of course, after a certain number.
Okay. Okay.
All right. So of course we don't have a perfect control of the probe. We can't really prepare the probe in a certain way and then shoot it through the plasma, right? So there is this limitation in this type of setting. So the jet is produced in a completely random way alongside the coagulant plasma. So this is one limitation. The other limitation is that the jet is made of the same and obeys the same dynamics of the coagulant plasma. So if the jet were to be, say, as I said, of lower energy, then of course we wouldn't be able to tell the difference between jet and jet. So what we want is a large separation of scales between the coagulant plasma, which is characterized by a temperature scale of the order of the GeV scale, and you want high energy jet, typically for the order 100 GeV, at RIC from 20 GeV, HC 100 to TeV scale. And as you can see how you can span really 3 orders of magnitudes in terms of scale. So it's really a rich physics. So we are able, using jets, to study different regimes of high density QCD dynamics. So you go from vacuum physics here, where you just observe jets that are coherent colored objects that propagate in a completely independent way. Then before reaching a thermal state where the coagulant plasma sits, which can be understood as if we have access to it, could help us map out the QCD phase diagram here. But in between, we have non-equilibrium dynamics. Of course, the jet interacts with the plasma. It will transfer energy on all kinds of quantum numbers from the TeV scale all the way down to the GeV scale. And then this dynamics of energy transfer is already something very rich and complex, and is also a consequence of involved QCD dynamics, which is worth studying. I'll come back to that later. All right, so we want to study coagulant plasma. We want to study non-equilibrium QCD dynamics, and to do that, we need, of course, to develop theoretical tools and also understand and be able to compute observables to reach the accuracy that is necessary to extract meaningful information. So we're talking about jet production. So I'll focus on inclusive jet production. So we have all kinds of observables, but this is the simplest observable, which is used to compute the nuclear modification factor. So we produce a jet, and from a heavy ion collision or proton-proton collision. And we need to be, so that we have a tool called factorization theorem that tells us that we can separate long distance physics that happens at the scale of the order of the confining scale on the QCD, and short distance physics that we can compute using perturbation theory, very weak coupling. This factorization theorem is given by this similar to the formula this form. So you would have a probability distribution, which is a Parton distribution function here, for having part All right. So we have the Parton distribution functions, all right, that are universal objects that we don't know how to compute. We know how they evolve with the scale via evolution equations known as Stiglab evolution equations. We can fit them in a certain process like deep inelastic scattering, and then use this property of universality to compute observables like jet production in proton-proton collisions. Okay, so we know these to a certain accuracy. We know the Parton distribution function. The hard matrix element, as I said, it's a completely perturbative object that can be computed order by order in perturbation theory. And of course, you measure a jet, you don't measure a quark. So you need another function, which is called the jet function, that tells you how to convert a quark, an initial quark, into a jet. So again, what a jet is, scale is in fact defined as a collection of hadrons that make up the total jet PT within a certain cone of size r, right? Typically a cone size, right? Depending on the algorithm, that it has a cone shape. So it depends on r, and it depends on the jet PT here. So this object can also be calculated perturbatively, right? Order by order in perturbation theory. However, when r is small, there certain estimation of large logarithms of the scales PTR may be required here. So there's also technology here in terms of freesoning to all orders, this type of branching processes that make up the jet that lead to the definition of this jet function. But this is known how to perform again to a certain accuracy, just by expansion in the coupling, powers of the coupling constant. All right, so we have three objects again. We have the Parton distribution function, convolution of the Parton distribution functions times the hard matrix element times the jet function. So now in heavy ion collisions, we'll have a similar factorization formula simply because the physics, the short distance physics, doesn't know about the yes.
So in the factorization, is the jet kind of a universal thing? Like, but you said there's no unique definition for a jet. So I mean, is there any kind of like algorithm dependence encoded in the factorization, or is it kind of taken to be a universal function?
So there is a dependence on the algorithm, but the universality is there. You can understand the universality of jets, especially concerning the. You go back here. So this jet function is universal because it factorizes out of the rest of the process. It's not dependent on the process. Whether you had a proton-proton collision or say E plus minus, jet function depends only on collinear particles. The particles that have been emitted and know only about the color charge of the parent particle. So it's only a function of this of the properties of this initial particle. And in that sense, it's universal, okay? Doesn't depend on the rest of the event. Other observables are not necessarily universal. If you measure more differentially, you might lose the universality of your whatever object you are measuring. Now, concerning the algorithm, then provided, of course, you have an algorithm, so you could always use the same algorithm, and you will have the same jet function in another process, right? But if you use a different algorithm, of course, this would modify even within the same process.
Can you repeat the difference between the heart function and the inclusive jet function?
Yeah.
Sorry.
Yeah, sure. So the heart function is basically just computing, hard matrix element involving, say, the elementary particles in the process, right? Suppose you have now, what is the leading order type of diagrams? Suppose you have a quark, two quarks that would interact, producing the jet. So you would have this kind of 2-to-2 matrix element, right? You would, of course, integrate over the wayside jet, and you measure the jet that's in here, right? So this would be process, which is alpha s squared. That's the leading order, right? Now, what goes into the jet function is all of the fine dynamics along the direction of the jet, right? So suppose now the jet is not only quark, right? So the jet is a bunch of particles. Suppose it radiates a gluon, right? A collinear gluon. So this collinear gluon, so long as it is collinear to the jet, well, you can say, well, this belongs to the jet, right? Because it belongs to the jet, it's going to be recorded as part of the jet function, right? Now, if this gluon, suppose you have another gluon that is radiated away from the jet, then you say, well, this gluon, I should maybe add it to the heart function as at the next order in perturbation theory. All right. So this gluon would be order alpha s cubed, right? But then, of course, there's an ambiguity in how, if you have a gluon sitting in between, right? In between, is it part of the jet or is it part of the heart function? And this is where the factorization and the dependence on the factorization scale comes in. So as you can see here, you have a dependence on mu in the heart function and dependence on mu in the jet function. And this ambiguity is encoded in the fact that the cross-section doesn't depend on this mu. So by varying mu, you can either account for certain type of gluons within the jet function, or so there's a crosstalk between the two functions through the evolution with respect to this factorization scale.
Isn't R also a kind of factorization scale for the jet?
It's not factorization scale, it's an actual measurement, it's a scale. But you're right, it's basically what's happening is the following. So you have two scales here in the problem, right? You have two scales. So you have the jet PT, let's call it Q, which is PT, right? This is the scale of the heart function. So all of the processes, the very hard processes happen here at a certain scale Q, right? And to the other PT, right? Then you have to evolve from this scale down to another scale where the jet function sits. All the collinear modes here, they live at a scale which is of the order PTR. Okay, so PTR relates to the transverse, the maximum transverse momentum that can be generated in a splitting, right? So indeed, you have two scales. One scale characterizes the jet function, and the other one the heart function, right? So, but the evolution, typically a Diglop evolution equation that reasons logs of this scale would come with the PT divided by mu here. And in here, you would have a log of mu divided by PTR. So if you do the calculation, you get an alpha s that's, let's say, 1 plus, and here 1 plus, and then mu would cancel out when you sum these two logs. So PTR can be viewed as an evolution variable because it comes alongside the mu. So if you take the derivative with respect to mu, you get the Diglop evolution equation with respect to R. But R is actually a measurement, is an observable.
Okay, thank you.
Okay, so this is for the jet. different proton collisions. Now things become a lot more complicated when we talk about jets and heavy ion collisions, right? So, well, let's start. Let's try to construct the say our understanding of jets and heavy ion collisions step by step. Let's start by saying that short distance physics is to some extent universal. It doesn't really know about what happens at let's say at the Fermi scale. So the hard matrix element should be independent of whether the process was whether we are studying proton-proton collisions or heavy ion collisions. So the existence of the quark-gluon plasma does not alter the Hard function. This short distance physics, almost instantaneous interactions. You can view it. So if the time scales it takes to form this type of process, the time scale t is of order 1 over pt. Okay, 1 over pt. You put numbers here, let's say 100 GeV, you get a tiny fraction of a Fermi. So it's instantaneous. So for the physics that occurs at the Fermi scale in here, the interactions that happen at the Fermi scale here in the plasma, for them, this is almost time zero. It's instantaneous. So hard function is, so now we need to, now we should expect the jet function now to be modified. And then we start looking at the scales. So we still have a PT, right? That's the jet PT R. But then we have additional scales in the problem. We have the plasma temperature, right? That's the, if you have a thermal plasma, it's plasma temperature. Also the system size. This is another dimension for quantity, the system size L. L is the size of your plasma. It's typically a few Fermi again. So, and probably more scales, emergent scales. You could construct scales based on this combination of temperature and the system size. But in addition to that, you could have the coupling constant, which can lead to the creation of the scales. So the question, one of the questions is, are the medium effects perturbative? I mean, can I just go and start using perturbation theory and compute corrections perturbatively? Or are they completely non-perturbative objects? In which case, I would need some kind of non-perturbative operator that I hope to be universal, that I can probably maybe compute on the lattice. So these are still open questions, but you can always assume a certain degree of weak interactions, given the fact that the jet is already, say, a weakly interacting object. It's made of high energy partons, and in the interaction, will have to obey a certain evolution equation that is perturbative. All right. So again, the other question is whether the corrections to this jet function are sizable. We know they are sizable simply because the RAA tells us, from simply empirically speaking, we see that the RAA is way below 1. So the interactions are order 1. So the interaction is very strong. And the question is whether we can compute those strong power, the large, possibly large power corrections that can be constructed out of medium scales divided by the jet scales, ETR. All right. So the typical transverse momentum scale here, which we'll encounter later, is Q hat L, and Q hat is the so-called jet quenching parameter, which is just a transport coefficient, which scales like the coupling constant G to the power 4 times the temperature cubed. So this is just a depiction of what could happen. So you would have, again, the same type of collinear radiation that are there just because you have a highly virtual state here that fragments, okay? So this would happen in vacuum. But then on top of that, you would have interactions with the scattering centers in plasma, multiple collisions here, which may also, so they could lead to deflections of your particles in the jet, right? So this leads to momentum broadening. And in addition to that, you could have also medium-induced radiation that lead to the increase of the number of particles in the jet. So this kind of processes are to be expected. All right, so now the elementary processes. So we first start, before we talk about inelastic processes, we have elastic processes. High energy parton can go through the plasma and can scatter off scattering centers in plasma. If the plasma is large enough and the mean free path is much small in the plasma is much more than the system size, then you could expect having many scatterings to happen, right? So for thermoplasma, the mean free path is given 1/g squared times the temperature here. And for again, if G is small enough, the correlation length in the plasma, which typically stands for the time it takes for scattering to happen, if this is much smaller than the mean free path, then we can talk about independent scattering process here. So we have each scattering is independent of the other scattering. So you can view this as a classical process where these multiple scatterings happen in a very independent way. So this is the approximation we usually tend to work in. Otherwise, the calculations would be untractable. All right, so the effect of multiple interactions would lead to the broadening of the transit momentum. Yes?
Very naive question on the previous slide, or actually also on this slide. What is a G? That's
So
parameter.
G is the QCD coupling constant.
Oh, okay.
So that it's a parameter of your the QCD Lagrange.
Uh-huh.
So it's related. So we usually use alpha S, which is, so I was using alpha S here, which is G squared over 4 pi. And this is the coupling constant.
Okay. So basically that epsilon D, the difference between epsilon D and the mean free path length just depend on that.
Say it again?
It's just like if on the previous slide. So the device screening length is 1/GT and the mean free path is just extra 1/G.
Yes.
So their separation is just kind of
Exactly.
controlled.
If G is small, then there is a separation. All right. This is the working assumption. We assume the interaction to be perturbative, so that the coupling which is associated with this vertex here. So there is a gene here. If G is small, then I would have this type of hierarchy, right? And G is small here if the momentum transfer Q perp is large enough. So the momentum transfer Q here needs to be larger than lambda QCD, and usually the coupling constant here depends on the scale at which this process happens, which is typically the transverse momentum transfer,
Okay.
right?
Gotcha. Thank you.
All right, so multiple scatterings would lead to the broadening of the transverse momentum. So again, we have high energy particle going through the plasma. The energy doesn't really change much due to the interaction. This is another working assumption. The energy is very high. We work in a very high energy approximation. The momentum kicks are very small compared to the energy. So there's barely deflected. There's a certain accumulation of transverse momentum. And this can be described by Brownian motion in transverse space, all right? So you have an accumulation of transverse momentum, and this happens in a random way. This is Brownian motion. And as we know, Brownian motion, so the mean squared displacement here in momentum space is linear. So this is so it's linear with system size or with time, right? So the KT squared grows linearly with system size, and the proportionality factor is this transport coefficient I mentioned before. So it's a crucial parameter in the theory of jet quenching. It's really the fundamental quantity that encodes properties of the plasma. By extracting this Q hat from the data, we can infer properties of the quark plasma. Another way of viewing this Q hat, this transport coefficient, you can view it as a gluon distribution of the plasma. It's really proportional to the gluon distribution. If I go back to this slide here, Q hat is associated with this elementary process here, and it's as if we had a certain gluon distribution in here, right? You pick a gluon with a certain probability that interacts with your high energy particle. Okay, so Q hat, well, it's given in terms of the mean free path and the biomass, as the biomass squared, parametrically speaking, divided by the mean free path, and it can be computed using the elastic scattering cross-section. So this elastic scattering cross-section, which is, again, this process in here, right? So the process in here, the cross-section goes like, the 2-to-2 matrix element goes like 1/QT to the 4th, right? So this is the process in here, right? Similar to this one. So the 2-to-2 matrix element 2 to 2 matrix element squared usually goes like g to the fourth, because we have to square this. We have a g here, we have a g here, we square this, and then it's divided by the momentum transfer qt to the power 4. All right. Of course, this is proportionality, not exactly. All right, so this is what we need this cross section, right? Because we are interested in the mean transverse momentum squared. We have to weight this by the transverse momentum transfer squared, and we integrate over transverse momentum. It's kind of measuring the average squared of the transverse momentum transfer, right? That's what Q hat is about. Rho is just the density of scattering centers. So you compute this, you integrate, and then you get g to the fourth times the temperature cubed, right? So here it is cubed. I need to correct it's cubed. All right. So this is a result of the leading order calculation. So this is Q hat, transport coefficient at leading order. If I measure it, I have access, for instance, to the temperature of the plasma, right? Okay, so in addition to still have about 5 minutes. In addition to elastic processes, we can have also inelastic processes. So by having a charge, we know that a charge that is accelerated changes direction or receives certain kicks can radiate, right, in QED, but in QCD as well, right? So the interaction here of this high energy quark that changes color states by interacting with the plasma can also lead to the radiation of additional gluons. Why is this process important? Well, this process is important because it can lead to additional energy loss. By radiating a gluon, the quark can lose energy and can be eventually stopped if it radiates enough gluons here. So the process so the process of radiation here is a quantum mechanical process. Not one scattering can lead to the production of your gluon. Okay, so you can imagine having one scattering happens once, and then you radiate, right? And then wait a little bit, and then you scatter another time, and then you radiate, right? But the radiation process is quantum mechanical, and it takes a certain time for the gluon to form. So this gluon to go on shell needs a certain time, which is called the formation time, right? And using the uncertainty principle, this formation time scales like the frequency of the gluon divided by transverse momentum squared, transverse with respect to the direction of the jet. All right. So this is the formation time of the gluon. But remember that we said that in the plasma, the transverse momentum broadens, right? Remember transverse momentum squared from the previous formula here? Said that the partons that propagate in the plasma should acquire transverse momentum of the order Q hat times the time, here's system size, but you can replace L by the time scale it takes for this momentum, transverse momentum to accumulate. So going back to this formula in here, right? So we have omega over kT squared. Then I just replace the transverse momentum squared by, do the math here quickly. So I have the formation time, which is equal to omega over k perp squared, right? Using the fact that k perp squared is equal to Q hat times during the time Tf, right? KT squared Q hat times the time it takes to accumulate this transverse momentum. It's Tf. All right, so then I can replace this in here, right? I can use this in here. It's Q hat Tf. All right. Now I can solve for Tf. Right? I have Tf on the right-hand side, on the left-hand side. Solve for the formation time. So this formation time is really the physics of the production of medium-induced radiation. Is equal to omega over Q hat, right? And then I just take the square root of this, which is just the square root of omega over Q hat. All right, so this is how the formation time of this gluon scales with Q hat, the questioning parameter, and the frequency. So low frequency soft gluons are formed over a short time scale, whereas hard gluons take longer to form. All right, so this is how this process happens, all right? So now, so during that formation time, okay, multiple scattering centers can act coherently to form that gluon. So for that gluon, all of those many scattering centers can act as a single effective scattering center. So in other words, the calculation, that naive calculation of saying that, well, the radiation intensity should be proportional to the number of scattering centers is wrong. The radiation is suppressed compared to that naive expectation that it should be proportional to the number of scattering centers. In fact, it's not. And this suppression is called the LPM suppression. It's the Landau-Pormez-Migdal effect, which is observed also in QED. So in QED, radiation is suppressed if the formation time of the photon radiation is much larger than the mean free path, such a way that many scattering centers could act coherently to form that photon, leading to the suppression of the radiative spectrum. So this happens also in QCD. And of course, there's maximum suppression that is achieved when the formation time is of order of the system size, and this leads to this characteristic frequency omega, which is Q hat L squared, which is another scale for medium scale that is important. If now I set this to be equal to L, right, by solving for omega, I get omega C, which is Q hat L squared, right?
Sorry, but that TF and the L are, I'm gonna assume, are smaller than the QGP formation time and because that happens, well, like jet forms before from the initial Howard scattering, forms before the QGP. But when I start radiating, that'd be before or after I have the QGP.
So this will happen inside the QGP. So
Okay.
after the formation of the QGP.
Okay.
So the formation time, so this radiation process happened with constant rate. It could happen anywhere inside the medium.
Okay.
Anywhere inside the medium. So it could happen, say this is the medium. Suppose this is, I guess I'll have to wrap up here. So this is the medium. This is going from 0 to L. You could have a radiation that happens here or here, all right? And the time scales is TF, right? So I have, in fact, a plot that shows that, but I can maybe jump right into it here. So you see in here, so you would have system size. So this radiation can happen anywhere along the medium with constant rate, with a formation time which is much more than the length of the medium, right? So okay, so I wrap up here by so we have certain characteristic scales. So we need to, so this helps us, this parametric discussion is very important, because without doing any actual calculations or, field theory calculations, we can estimate and extract some scales. We learned about Q hat, we learned about this characteristic frequency omega C. We could even estimate the radiative spectrum. All right. So before I go to the next slide, I wanted just to give you here a sense of how the size of the scales. So for Q hat, which is typically 1 GeV squared per Fermi, and the medium length, let's say 5 Fermi, we get an omega C, which is 125 GeV. So this tells you that with these realistic numbers, you get a hard scale, a large scale out of the medium, which is omega C. This is very important, which is in line with the fact that jet quenching is an order 1 effect. All right. So let me wrap up this first lecture by just showing you the actual medium-induced radiation spectrum, right? So let's go back in here, right? So quickly, and I will give this. So what is the radiative spectrum? Well, the radiative spectrum is D. Well, omega here is completely conventional. Di over d omega. So this is the radiation spectrum. So we know that there is a rate, the coupling constant here, alpha s, because we are radiating. So there's an alpha s here. We know that this happens with constant rate along the medium, so it has to scale with system size. It happens anywhere along the medium with the same probability, so it has to scale with system size. And just to have, because this is a dimensionless quantity, I need another scale to make it dimensionless here. And then I guess you can guess it. The only scale I have here from this physics is the formation time of the gluon, right? So it's going to be TF, just by scale analysis. Scale analysis, this is what I get, all right? So L divided by the only time scale in the problem, which is the formation time. And then if I replace TF in here with the scale that I had here, which is TF equals square root Q hat over omega over Q hat, right? If I use this, then I get that square root Q hat L squared. If I put L squared inside the square root here, I get Q hat L squared divided by omega, which is again alpha S square root omega C over omega. So the spectrum drops as 1 over square root omega. Remember the approximation where we assumed that we had independent scattering centers without no coherence. With no coherence, we should have a flat spectrum here. The fact that it drops like 1 over square root of omega, this is this LPM suppression, which is due to the fact that more and more scattering centers act coherently as the formation time increases with omega. You have a question?
Wait, by 125 GeV suppressed? Let me see if I'm sorry, just making sure.
So this is just a scale that is, in fact, this is the upper end of the spectrum. This is omega C. So above omega C, you have a strong suppression. So you can forget anything that happens above omega C. So the medium, the maximum frequency that the medium can produce is omega C,
Okay.
which is 100 GeV. So, and the lowest frequency is of the other temperature scale, right? So we go from 1 GeV to 120 GeV. And this is the spectrum that spans these two scales, from the GeV to the, and this is this is the bulk of the radiation, which is in between this temperature scale and omega C. This is the regime where the formation time here, multiple soft scattering approximation, where omega is between the temperature and omega C, and the formation time is between the mean free path and the system size. All right. So let me conclude here this first lecture by saying that, well, things simplify here, because now we know that the dominant effect will come from radiation that has formation time, which is much smaller than the system size, which is in between here, much smaller than system size, okay, yet larger than the mean free path, and it happens with constant rate. So I can use this to kind of build up my all-order calculation for energy loss. So I have the elementary process that is responsible for the jet to lose energy by radiation, and I can go to higher orders and compute the probability distribution. Yes?
But sorry, but then the medium itself is also not static, right? Because as I keep going, then QGP increases, temperature is changing.
Yep.
Wouldn't that also, would that be true at the beginning of when I've created the system? Does that also evolve, or is it?
Yes. Okay. So you could, so here, of course, we are assuming a brick, right?
Okay, yeah,
homogeneous, right? Just for the sake of this parametric discussion.
Okay,
But
sorry.
in principle, the medium dynamics should be encoded in the time dependence of the quenching parameter Q hat.
Okay.
So Q hat depends on the geometry, depends on the dynamics of the plasma, and this will be reflected in Q hat. So Q hat will decrease as a function of time, and so will the radiation spectrum. So this is a radiation spectrum, and I think this is the perfect timing to stop this first lecture after I've introduced the elementary processes. And tomorrow we will discuss how we go about, using this knowledge to understand the energy loss in the coagulant plasma and apply it to the actual observable, which is the nuclear multiplication factor.
Let us thank. More questions or comments? Had some discussions so far. Go ahead.
So are you not including quark exchange with the medium because it's energy suppressed?
Yes. So the approximation, this is a high energy approximation. So we're assuming the energy of the jet partons to be much higher than the momentum transfer. And in this kind of kinematics, which is called the Regge kinematics, the 2-to-2 process is dominated by the gluon exchange. And quark exchange are suppressed by powers of the jet energy. They could be included, but they are higher orders of technology.
This graph has a certain analogy with a transfer function of the describe a medium, because there is like these bold diagrams that when you pass through a pole, they change the characteristics of the curve. Is there as an analogy?
Say it again, I'm not sure I got what
In
you.
this kind of plots, is there an analogy with like a bold diagram of a transfer function of the medium? Do you know?
I'm not familiar with the.
Okay. Because when you write an lecture function for the transfer function, when it passes through a pole, the a pole of the function,
For what? I don't.
like the denominator of the, if you have an expression for this kind of,
You're talking about propagators here.
yeah.
One over. Yeah. So you're referring to the point of the propagators, right?
Yeah.
Okay.
I just was wondering about if there is any analogy that you can make, because when you look at the transfer functions, when you plot it in a bold diagram, sometimes you can look at the curve that they make in the when you pass it through a pole, the curves has this kind of behavior. So probably
I'm not sure. I haven't thought about this way, but yeah, I'm not sure there's a connection. But maybe I don't know if it's kind of related to this, but indeed here you have a pole because you have propagators, but we are in the regime which is called the Glauber regime, where the denominator is given by kT squared. So the k, the energy is much smaller. Energy transfer is much smaller than transfer momentum. So the denominator goes like 1 over kT squared for the propagator in the T channel.
I have a question about timescales. Could you go to slide 14?
14.
Yes, so here in the right-hand picture. So here we have two protons attacking each other and then producing the gems, and around it is the quark-gluon plasma. So my question is on which timescales does the plasma form? Because when I think about it, and if I go to higher and higher energies, the individual reactions among the protons that form the quark-gluon plasma should have a more and more significant boost, such that there is no more. So if you get to very, very high energies, at some point these should all spread out so fast that there's no medium to transverse through one. Or is this picture wrong?
So the first of all, the time scale for the formation of the quark plasma is believed to be, so you will immediately instantaneously form a high density say medium right after the right. The question is whether this medium is the actual plasma we're talking about. There is a stage, a first stage, where the medium heats up. We have different stages for the this kind of non-equilibrium thermalization process. And usually it takes about, let's say, about a Fermi. That's what is believed before hydrodynamics behavior or dynamics to become important. Let's have in mind like about half a Fermi to a Fermi if you want a number. Okay? This doesn't mean that you don't have strong interaction for that. So this is typically the time scale. But then, of course, because of Bjorken expansion, this will dilute, right? So the strength of interaction will go down. So there is some kind of sweet spot, a Fermi scale, Fermi to Fermi, where the plasma somehow is heats up at very high temperature and leads to strong interactions with the gel. So before that, the plasma is not formed, and after that, it's going to just decay.
So going to the FCC and going to higher energies wouldn't help you understand the quark-gluon plasma anymore? Or is that wrong?
So the FCC is for E plus minus, right? Or was it?
Well, okay, so that doesn't have to be the FCC. Just so I was thinking about the extensions of the LHC. That there's a couple of proposals, of course, and all of them are, well, at least one of them was like a larger storage ring for higher energy conditions, right? So would this then help understand the quark-gluon plasma or not?
What type of processes are going to be studied there? It's, I guess, C plus minus, or is it, so you could, in principle, if you understand very well the interaction, let's say the fundamental interactions that are involved in creation of quark plasma and also interactions of high PT partners, then you could imagine having a quark plasma factory, even in proton-proton collisions, or even in smaller systems, if the energy is high enough. If the energy is cranked up, you could imagine producing quantum plasma in any system. Right? That's just a question of energy density. And then the question is, right? So the question is whether we can reach those energies and whether the dynamics are going to be similar to this kind of heavy ion fission interactions, where the system is by construction much larger. So you're going to learn different things based on probably the same type of dynamics.
Let's thank is in once again. 30-minute break and it's 15 to 11.
Couple announcements. Let's see, as we come to the end, the schedule tomorrow, we've got some openings for some student talks in the afternoon. The Friday barbecue is canceled. Chemistry couldn't get a quorum to put that together. And tomorrow after lunch, we'll trade your meal card for your certificate of participation.